All right, yeah, let's take a look at how to add vectors. And in this video, we're going to do the geometric or graphical way, and then we're also going to do the algebraic way. So one of the graphical ways of adding vectors is using the parallelogram method. Okay, so basically we have two vectors here, and the kind of keynote part of the parallelogram method is that the two vectors, their tails meet, right? They're connected. And then the resulting vector is this kind of projection up here. So let's just work through an example so it makes a bit more sense. So let's just say that's vector A. And then let's just say that, I guess the first example, that's vector, I'll pick a different color. And then this can be vector B, okay? So let's just draw vector A. Woo, I don't know. Do your best to kind of match the magnitude as well. And then we're going to draw vector B. Remember the tails, the tips, no, the tails have to, and then what we're going to do here is you want to like kind of project or extend this so that it's parallel to this, right? A parallelogram, the two opposite sides are parallel. So it's going to kind of just be like an imaginary, we're going to imagine like there are lines here. And then the resulting A plus B vector would be this guy right here, from the tails outwards, like that. Okay, so that's how you would add these two vectors. Let's take a look at a different set of vectors where we can let this be A, and we can let that equal B. They don't have to be the same magnitude either. I know I'm drawing them, it can be like that. Okay, so let's just draw vector A here. Remember, with the parallelogram method, these parts connect. And now this is a kind of hard one to draw, but remember, from here we just want to project it so that it's parallel and equal in magnitude. That's something I didn't say earlier, but equal in magnitude, because it doesn't just extend out to like out here. It needs to extend kind of over here, where it would be if there's a parallelogram. And then here, just extend it out like this. So then looking at here, right, the resulting vector starts at the conjunction of these 2 points and extends out to the opposite kind of diagonal that we get when we draw this. So that's the resulting vector. So this is the parallelogram method. It's the harder of the two methods, but you have to know both. The tip-tail method's easier. Let's just say that's vector A. Let's just say that's vector B. The way you do it is vector A. And the difference is that you just actually try and see if you can figure out yourself. When you learn it yourself, it's more satisfying, but then I'll explain it. So the difference here is that it's literally like the tip to tail. This part, or this part here, connects with this part here. Like you literally can just move this vector over, so it's kind of like that. And then the resulting vector is drawn from this to this, right? So just like this. And I don't know if I need to mention this, but you're allowed to move these vectors around, right? Because a vector doesn't ever have like a set position in a coordinate space. It always just has a direction and magnitude. So you're free to move it wherever you feel is right. Let's do another example. Let's just say that's A. That's B. Sorry, I picked blue. It was the first thing I saw. Vector A, kind of like this. Tip tail, we're gonna put blue pointing down like that. Do your best to approximate the magnitudes too. And then the resulting vector, I'll do it in black to stay consistent. The resulting vector looks like that. Okay, so you just travel along that path. So basically you're starting here. Kind of think of it like displacement, I guess, maybe. You travel along this path and you end up here. So the arrow is just the true path, or the true, I guess, motion that you take is just from there to there. Okay. And then I guess this is probably a good thing to try. So we have these two vectors. So this is what the resultant vector looks like with the tip-tail method. And just to prove that the two methods are equivalent, I'm gonna do this. we're going to get the tails to touch, right? So this is exactly like we do in the parallelogram method. And then we're going to just kind of try our best to really project this here, and that's the resulting vector, right? And obviously these vectors are not identical, these vectors that I've drawn myself, but these vectors algebraically, you'll see, are going to be identical, and they look relatively the same, but obviously human error has made this, but I mean, you can see how they're equivalent. I hope you can see. So now the question kind of comes, how can we do this thing algebraically? Because you're not going to be able to draw this in a 3D coordinate space. It turns into a pain, but it's important we learn graphically. But anyway, algebraically. So how do you add two vectors? So let's just say we have vector A with, and I just picked 3 coordinates. It could be 50 million coordinates if you want, or it could be 2. It could just be an XY, but I picked 3 because that's what you're probably going to be dealing with. So let's just say the vector A has these coordinates. So this x, y, z, kind of from the origin, it'll go out like that. And then this point will be x, y, z. Or, sorry, in this case it would be A1, B1, A3. Sorry, I just wanted to make that obvious. Same thing for B. Let's just say B goes out like that. And from the origin. So they're both going from the origin. And this point is B1, B3, B2, B3. Okay, anyways, so when you're adding these things, it's really basic. You just A1 plus B1 gives you the X component. A2 plus B2 gives you the Y component. A3 plus B3 gives you the Z component. Let's just take a quick look at an example, and then I feel like that's pretty much it. This isn't anything new. It's literally just algebra. So let's just say vector A has the components. So this is adding vector components. 5, 4, 3. Let's just say vector B has -1, -3, 4. These are the components, right? And this is how you express the components. Sometimes you can do this like a matrix. So anyways, we're going to do A plus B. A plus B. Sorry about the handwriting. I'm still writing on a trackpad. Equals, what's 5 plus -1? 4. 4 plus -3, 1. 3 plus 4, 7. So the resulting components, when you add these two vectors, is 4, 1, 7. So then if we want to put this into a actual vector kind of thing, 4i plus 1j, we could leave the 1 out, plus 7k, right? Because these are the vector parts, these letters that I put in, the unit vectors, they're what make it have like a direction, but these are just scaling. So that's something that you don't want to forget. But yeah, I hope I helped.